So let's look at this next problem. We have potassium chloride dissolved in water, producing a total amount of 65 grams of solution and a temperature change from 22.5 degrees Celsius to 20 degrees Celsius. The specific heat is 0.8 calories per gram times degrees Celsius. So it's asking, is this dissociation endo or exo? Okay, and it should also be asking, forgot part of it, calculate the heat. So instead of what, let's write calculate the heat. Because what's the point of all these numbers if we're not going to use them in a calculation, right? So calculate the heat. So two questions like the last one, okay? So endo and exo, all that means is it's shorthand for endothermic and exothermic. If we have to calculate heat, we're going to use that equation where Q is equal to MC. And instead of writing delta T here, the change in temperature, I'm just going to go ahead and write that TF minus TI that we looked at on the previous question. All right, so let's write my list of knowns. What do I have here? All right, well, I have 65 grams. So looking at my variables, that would be my M, my mass. So that's how much total solution is made when we dissolved the potassium chloride in water. Sorry, you can probably hear my kids playing outside. Okay, so continue reading and we get a temperature change. So once again, we have two temperatures and what we need to figure out is which one's final, the TF, and which one's the initial, the TI. So reading it, it's starting from 22.5 to 20. So our initial is going to be the 22.5 and the final then is going to be the 20. I'm going to tell them to be quiet on the next one. All right. TF is 20, that's where the temperature is ending. TI is 22.5. Okay, so the last variable that we need to solve for heat is this C value, the specific heat, and that is given to us as 0.800. I'm going to leave off the units. So, have everything we need, let's plug it into the equation. So once you decipher what all these numbers are, what variable they belong to, it's really just a matter of plugging it in at that point. It's not too bad. So my C value this time is 0.8. My final temperature is 20. My initial was 22.5. So notice what's happening here is the temperature is actually decreasing, right? The object's getting colder, so that's going to help us answer the endo or exo question. Before I do that, let's plug this in and see what we have for heat. 20 minus 22.5. Negative 130. We're looking at 3 sig figs, so I am going to simply put a decimal point after that 0 to make sure it's counted. I don't know why I wrote 180 when I said 130. Okay. See, I need you guys here to do the calculations for me. All right. So negative 130. So notice a few things with this answer. Okay. First off, notice that it doesn't have units and add them. It's calories. So heat is measured in calories. But the other thing, notice it has a negative sign. That's okay. Heat sometimes has a negative sign. This negative sign can help you answer the question of is it endo or is it exo? Because on the previous one we said if Q was greater than 0 or positive, we have an exothermic reaction. If the Q value is less than 0, we have an endothermic reaction. Okay, so in this case, it's the latter, right? The Q is less than 0, it is negative. So this reaction is in fact endothermic. Now, if this is hard for you to remember, then just look at what's happening with the temperatures. Ask yourself, is it getting colder? Is it getting hotter? If it's getting colder, You can feel it get colder in your hand like it is here, right? The temperature's going down from 22 down to 20, so you would feel it get colder. That's because it's absorbing heat from your hand, making your hand feel cold, and that is the definition of an endothermic reaction. The first question that we're going to look at is how many calories of heat are produced or absorbed when a solution of HCl and NaOH are mixed, resulting in a total mass of 50 grams. So it's a large word problem, so we need to pick out some clues that will help us solve. So first off, it's asking us to solve for calories of heat. Okay, so that is that Q value that you might have saw in the PowerPoints. So when you're looking at equations, it's the Q is equal to mc delta T. So Q being the heat, and it is measured in calories. Okay, so we're mixing HCl and sodium hydroxide for a total mass of 50 grams. So this number might be useful as well. So I'm just going through and kind of underlining things that are going to help me figure this out. Next, it says the temperature changes from, so I have two other values here in degrees Celsius, so I'm going to underline those as well. The specific heat is 1 calorie per grams times degrees Celsius, so another number. And then it asks another question at the very end, is the acid-base reaction endothermic or exothermic? So we'll worry about that question at the end. Let's focus on the first question, the word problem posed, and that being the calories of heat. So I'm going to write my list of knowns and unknowns that I have here. So the first number I encountered was 50 grams, and that was a mass. So it's going to represent the letter M in this equation. So mass is going to be 50 when I insert it in that equation. Grams is the units we want it in, so I don't have to do any conversions with that number. Next, the temperature changes from 21 to 29.5. Okay, so that's this delta T here. So whenever you see a triangle in mathematical equations, it means delta, and what that means is change in. So this delta T here means change in temperature. And whenever you have change in something, it's always the final minus the initial. So delta T is the same as if we were to write TF minus TI. So TF being final temperature minus TI being initial temperature. Okay, so these two temperatures given, one's our final and one's our initial. So we need to figure out and label appropriately what variable these numbers stand for. So it's saying it goes from 21 to 29.5. So the final is going to be the 29.5 because that's where it ended. So I'm going to label that over here as my T sub F, my final temperature. And I'm already writing the wrong number. Got my little eraser here. 29.5. So the initial then is 21 because that's what the original temperature was of the solution initially. So we have 21.0. So we have our M, we have our delta T, TF minus TI. We still need the C value. So that's going to be the last number that we underlined here. Okay, that C stands for specific heat. So specific heat varies depending upon each substance. So this number will always be given to you. So my C is 1. All right, so let's plug this in and solve for Q, which is calories of heat. So I'm going to rewrite this equation. Instead of having the delta T, I'm going to insert the TF minus TI. That way I can just plug in my values directly. So plugging in, I have my mass of 50. My C value, the specific heat, was just 1. My final temperature, we said was 29.5, and the initial was 21. So calculating this, I get 50 times 29.5 minus 21. Make sure you're putting that change in temperature in parentheses so that you're doing the subtraction first before the multiplication. And I get 425. So what are we looking at for sig figs? It's looking like 3 significant figures. So 425 calories are produced. Calories of heat are produced when we mix these two solutions. Okay, so now that we've solved for the initial problem, let's look at the last question in the word problem, and it's asking, is the acid-base reaction endothermic or exothermic? So when we talked about the definitions of endothermic and exothermic, exothermic was when heat was being released, so you would feel the flask get warmer in an exothermic reaction. Endothermic, however, is when heat is absorbed. So that would be if you were holding the flask, your hand would get colder. And the reason your hand would feel colder is because it's absorbing heat from your hand. Okay, making your hand feel colder. So in this case, well, let's look at the temperature change. That's what's going to help us figure out if it's endothermic or exothermic. So it's going from 21 to 29. So the temperature is increasing. So if you were holding that flask, you would feel it get warmer. So if it got warmer, it's releasing heat, and it is an exothermic reaction. Okay, so exothermic. Another way you can figure that out is simply by memorization. And what I mean by that is if you have positive Q values, so if the heat that you get is positive or greater than 0, it is going to be exothermic. If your Q values are less than 0, so if you get a negative Q value, that means that the reaction is endothermic. So notice this is the opposite of enthalpy. With enthalpy, positive values always meant endothermic and negative values meant exothermic. So it's the flip of the enthalpy rules that we saw in the PowerPoints. So that's why, to remember it, I kind of like to envision, okay, is it warming up? Then it's exothermic. Is it cooling down? Okay, then it's endothermic. Then I don't have to do this memorization. But do what works for you. And let's try another problem. All right, so now we're going to look at Le Chatelier's principle and apply it to this balanced chemical equation. So with Le Chatelier's principle, we talked about equilibrium reactions, and that's what this symbol here is. Notice the arrow is not going from reactants toward product, but it's also going back. So one's going toward the products and the other arrow is going towards the reactants. So that is showing that this is an equilibrium reaction. And with equilibrium, what happens is if we disturb anything in this reaction, what's going to happen is that equilibrium is going to shift to make a balance again, to make an equilibrium. Okay, so there are several different stressors or disturbances that we can do to disturb this equilibrium. And if we disturb it, all that's going to happen is the equilibrium will shift to make up for it and come back to its original state. So let's look at this first one. And I know I did this on the PowerPoints, so if you've already seen this, it's the same problem. You can just ignore this part of the video. But if I wanted to increase the concentration of solid iron, so that means I'm going over here, so I'm going to find solid iron, and that means that I am making that go up. So I'm increasing it. I'm adding extra solid iron to the flask. Okay, well, what's going to happen is I have now disturbed the equilibrium. So it's going to shift to fix what I did. So since I added more iron, it wants to get rid of that excess. And to get rid of that excess, then it is going to shift the reaction to the left toward the reactants. Because if it shifts towards the reactants, what's happening is it's going to get rid of that excess that I added. And it'll make more than of the iron 3 oxide. All right, so let's look at the next stressor. So this time increasing pressure. So if I'm increasing pressure, this is only going to affect reagents that are gases. So that's what I'm looking for. I'm looking at these little symbols and I'm seeing if there's any gases present. And there is. Oxygen. Okay? So if I'm increasing the pressure, what that's doing is it's going to increase the gas. Because we talked about how pressure can make gases more soluble. So by increasing pressure, what I'm doing is I'm increasing the amount of gas. So it's similar to what we did in the last one. I'm increasing one of the products. So if I increase one of the products, I've now disturbed equilibrium. The equilibrium is going to shift to get rid of that excess that I have now created, and it's once again going to shift toward the reactants to the left to get rid of that excess. Next one, raising temperature. So if I'm raising or decreasing the temperature, doesn't matter. What I'm looking for in the reaction is where that heat symbol is. Okay, this heat symbol, that's those Q values we were just calculating, how many calories. Okay, so if I'm raising the temperature, I find where the heat is in the equation, and if I'm increasing temperature, that means it's going up. Okay, so if this goes up and it's on the reactant side, I've disturbed the equilibrium, so it's going to shift the opposite direction to get rid of that excess that I just caused by raising the temperature. So heat is increased, equilibrium will shift, this time towards the right, toward products to get rid of that excess. All right, well, we've looked at several examples and they're all increasing something. So this last one is decreasing or removing. Okay, so in this case, it's the iron, solid iron. So I'm looking at solid iron. But this time what's happening is I'm removing it as it's formed. It's a solid, I can do that, right? I can take some of the solid iron out of it as it's being formed. So if I'm taking some of this away, that means it's decreasing. And decreasing something also affects equilibrium. It wants to get back to where it was. So since I took some of this away, equilibrium is going to shift toward what I took because it wants to replace what I took. Okay, so this time, since I took iron, it's going to go toward the products, toward iron, to make more of the iron that I took. Let's look at one more example. How about instead of raising temperature, let's add a 5. Let's say I am decreasing the temperature. So I'm putting it in an ice bath, let's say. Okay, so if I'm decreasing the temperature, I'm still looking for heat, so anything to do with temperature, I'm finding wherever heat is in the equation, and it's on the reactant side in this particular equation. Okay, so I found the heat, but this time instead of increasing it, I'm decreasing it. It's going down. So if it's going down, that's very similar to when I took the iron, because what I'm doing by decreasing the temperature is I'm taking that heat away. If I take that heat away, I have disturbed the equilibrium, and it is going to shift to replace what I took. So it is going to go toward the reactants, toward the heat, to replace the heat that I took by decreasing that temperature. All right, so let's try to write some generalized rules here to kind of help us figure these out in the future. So if you are increasing anything, whether it's increasing pressure, increasing concentration, increasing temperature, heat. If you are increasing the equilibrium will shift away from that reagent, or the opposite direction. No, I just spelled opposite wrong, but bear with me. To get rid of the excess. Okay, so if I increase heat, it's going to shift away from the heat to the right. If I increase the concentration of this iron 3 oxide, brain blip, it's going to go away to the right to get rid of the excess. But now, if I'm over on the product side and I decide to increase the iron, well, it's going to shift the opposite direction to get rid of the excess, this time to the left. Same with oxygen. If I increase the concentration of oxygen, it's going to shift towards the reactants to the left to get rid of that excess. However, if I am decreasing something, equilibrium is going to shift toward what I took. To replace what was taken. Sorry, trying to find something to do if you can hear that in the background. Okay, so decreasing. That means if I lowered the temperature, equilibrium is going to shift towards the reactants to replace the temperature that I took. If I decrease one of the reactants, it is going to shift toward the reactants to make up for what I took. But if I go over here and if I decrease either one of the products, it's going to shift towards the products to make up for what I took. Okay, so I hope that makes things clear. I'm also going to post a video that I've used in the past. It's not of me, in case you're not understanding the way I'm teaching it, a supplemental video on the Chatelier's principle that really shows some neat diagrams and things to kind of help bring this point home.